So, okay. So let's start with what is MPC, or what is multi-party computation. MPC is it's a well-researched subfield of cryptography. Really, in the mid to late 80s, they began this research around this question. There's been thousands, literally thousands of research papers, but it was purely theoretical until recently. So it depends how you define recent, but in 2010 or about 10 years ago, there was very little you could really do practically. There were very powerful feasibility results, a lot of beautiful research, but it wasn't something that you could really think about deploying. And then there was, over the last decade, there's been a very significant research effort to make MPC efficient enough to use in practice. And now actually we can, and it is actually being deployed. And I'll talk about some of that today. So it's very active in terms of the applied area of research, but also now in commercialization efforts. And the idea behind MPC is very simple. We want to compute on private data without revealing anything. And that's all we want to do. Can we actually carry out these private computations? The difference between something like fully homomorphic encryption is that MPC uses interaction. So we have these parties interacting, and we want to compute without revealing our private data. So let's just start off with a simple toy example, just so that we can get an understanding of the type of things that we're doing. It's really a toy example, but I think it's nice. So we have three cryptographers who want to compute the average of their salaries, but they don't want to reveal their salary to anybody else. And if you can see the numbers here in the slide, the salaries are so low that they really just don't want anybody else to know that as cryptographers with PhDs, this is all they're earning. So how can they essentially compute this without somehow giving their values to someone else? And it seems to be problematic, because you have you want to essentially just add the numbers together, right? The average and the sum are the same up to multiplying or dividing by 3. So they want to add these numbers together, but without anybody seeing anything. So how can you add numbers without knowing what you're looking at? So Alice starts, and she chooses a very large random number. For example, 652,195, and she adds that to her salary and sends the result to Bob. So Bob gets 772,195. Now Bob gets this number, and the first thing you should think about is that this doesn't really reveal very much about Alice's salary. And in particular, maybe Alice earns $100,000, but she chose a different number. She chose 672,195. So the fact that he got this value doesn't reveal Alice's salary. The next thing that Bob does, Bob takes that number and adds his salary to it and sends it to Eve. So now Bob adds 105,000 and sends 877,195 to Eve. And Eve, once again, doesn't really know anything at all because she just gets this number and she doesn't know what that big random number was in the beginning. Eve then adds her salary to that and sends it back to Alice. So Alice now gets 942,195. And Alice can subtract the initial random number that she used and divide it by 3. So now it's 96,666 is the result. And that indeed is the average salary of the three cryptographers. It's clear that Bob and Eve did not learn anything by what we said. But what about Alice? So with Alice, the way you should think of it is all she really got to see was the sum of all three salaries. And that's actually what she's supposed to learn. So she knows nothing about the Bob and Eve salary, which one is higher or lower. This is something that she cannot learn any information about whatsoever. So this is a protocol that's secure as long as at most one out of the three cryptographers is corrupted. Well, if two are corrupted, that doesn't matter because the average would reveal the third, so it doesn't make a difference anyway. So that's just a toy example, but what do we mean when we talk about MPC and MPC security? We really want a computation amongst a set of parties who want to join, some joint function, whatever they want to compute, while ensuring two main properties. There are actually more, but these are the two most important ones. The first is privacy, which tells us that nothing but the output is learned. So you should learn the average of the salaries, but you shouldn't learn anything beyond that. And it's important to note that the average of the salaries actually reveals some information about the salaries, right? So if Alice earns $120,000 and she sees that the average salary is $96,000, then she knows for sure that at least one of Bob and Eve earn less than her. But that's something which is revealed by the output, and the output is what we're supposed to compute, but you shouldn't reveal anything beyond that. The second thing is that the output should be correct. Right? It shouldn't be possible to somehow compute something which is incorrect. You could think about an auction or an election. Say, an election, you wouldn't want the candidate who got the minority to come out as the winner, because that, well, in most countries, you wouldn't want that. So that is the correctness of the function being computed as well. And all of these should be guaranteed, even if some of the parties are cheating, are behaving as adversaries. And that's the basic security properties that you want. When we talk about adversarial behavior, though, there are two possible or two main models. There are more, but two main models. The first is what we call a semi-honest model. And here, essentially, the adversary is running the correct software, but they should not be able to learn anything by looking at the transcript of what's being sent. So actually what they see, they can look at everything that's being sent and received, and they shouldn't be able to learn anything from that, but we trust that they're running the correct software. Why would, what would that model? That may model situations like two hospitals wanting to collaborate. No one thinks that one hospital is going to try to steal the private information from the other hospital. But for regulatory reasons, they're not allowed to pool their health data. So they could think about a semi-honest model where essentially they trust each other, but just not allowed to reveal anything. And indeed, semi-honest security models something what we would call inadvertent leakage. You know for sure that nothing about your information is being leaked, and you don't have to worry about someone else learning something about your confidential information. But in general, we do want to think about stronger security models, and then we talk about malicious adversaries. So this is an adversary who can run any software. They can run anything that they want. They know the protocols and the design, and they still should not be able to learn anything. So this is the more classical type of adversary. We have a set of 50 people. They want to compute statistics on their salaries. And even if in some of those, a subset of those collude together to attack the protocol, and they run some specific code which is written just to attack the protocol and learn more information, we have a proof of security that that's impossible to do. And there are two main settings also in terms of the corruption. We can talk about if the adversary can corrupt any number of parties. So it could corrupt all but one, and that last party should still have security guarantee, depending on what the function is. Or we can talk about something called an honest majority, where we assume that the attacker can only corrupt up to or less than half of the parties. There are some variants on that as well, but typically, obviously, a dishonest majority model is better because you get resilience and security against more corruptions, but it's also more expensive. So it sometimes can be a trade-off. There are cases where you can accept an honest majority, and then depending on your threat modeling, and then that gives you more efficient protocols. And of course, like with anything that's in the rigorous cryptographic methodology, we mathematically prove security against a mathematically rigorous definition. So how can we define this notion of security for MPC? And it's actually not that easy, because in encryption, we say something very simple. If you see encrypted data, you learn nothing, except for maybe the length of the message. And it's not that difficult to model learning nothing, although it's also not that easy. The first definition of security for encryption was only in 1984. But we can model this notion of not learning anything. But here you are learning something. You're learning your input. You're learning the output, sorry. And not only that, that output depends on your input. And you could be a corrupted party providing input. So this becomes very messy to try and define. And the way we define it is by thinking about what would the ideal situation be. Now, we all live in our modern world. And I guess we can all agree that our world is, our real world is not ideal. So this is just a sort of a mental experiment in order to define security. So let's think about what the ideal situation would be. Here we have Alice and Bob, and they want to carry out a computation. And ideally, there is a trusted and incorruptible third party that they trust and really cannot be corrupted. And if such an entity existed in the world and couldn't be corrupted, then the parties could just send their inputs to that trusted party over perfectly secure communication channels, which also don't exist, but it's part of our mental experiment. That trusted party can compute the output and just send it back to both parties, right? This would be a great world. If we had trust in the world, we would be able to solve our private computing problems very, very well, right? Very easy. Send your input to this trusted party, they do the computation, and they give you back the output. Now, just to understand and appreciate why this really does make sense, we talked about privacy and correctness. Well, clearly, in this ideal world, the parties learn nothing but their output, because that's all they saw. They gave an input, and they got back their output. Okay, that's they can't learn anything beyond it because there was nothing else that they saw. And correctness is also clear because this incorruptible trusted third party computes the function correctly because they're trusted and they're honest. And that means that we have a guarantee of correctness as well. So in this ideal world, our basic properties are preserved. They're actually more independence of inputs, and we can talk about in some settings things called fairness and guaranteed output delivery, but I don't want to complicate this more than I already have to. So in the real world, unfortunately, we don't have trusted parties, either because there's no one that we all trust, or more importantly, even if we all do trust Rand, we don't know that Nigel won't break into Rand's computer and therefore be able to result in, to steal information. So trust is not just understanding that somebody is not a malicious person. It's also understanding that nobody else can breach. It's accepting that nobody can breach them. And since everybody is breachable, we don't have any trusted party in the world. So in the real world, the parties just interact with each other, they send messages to each other, and they get some output at the end of the protocol. And the definition of security for MPC is that an MPC protocol must behave like an ideal world protocol. In the ideal world protocol, you just sent your input and got your output. And what that means is that an attacker can't do any more in this real interaction in this real world than it could in the ideal world. And because in the ideal world, the only thing you can do is choose your own input and then get back the output, that means in the real protocol, the most you can cheat is just to choose your own input. And arguably, or at least in many scenarios, you're allowed to choose your own input, right? When you're voting, you're allowed to choose who you want to vote for. When you're in an auction, you're allowed to choose the amount of money you want to bid for that product. But it does mean that if we're comparing our DNA to see if we're related, then we'd have to understand, do I have any interest in changing my inputs? So for example, Nigel is giving away $1 million to his, he knows he has a long lost second cousin, and there are actually algorithms you can run to compare DNA to see if people are related. And I tell Nigel, I'm your long lost second cousin, and here, let's run an MPC on our DNA in order for me to prove that to you, right? Because I don't want to give up my DNA, obviously. So I would actually have an interest in maybe changing my DNA because I want the result to be that I am that long lost cousin and get Nigel's $1 million. So sometimes, just the issue of input, choosing your input can be an issue. In many cases, though, that's just allowed, and so it's fine. So what are the definitional advantages? And this is, I think, a really important slide. When we think about this ideal world, this enables us to use MPC without being a cryptographer. You don't need to care at all how this MPC protocol works, because all you need to do is to build your application, assuming you have a trusted party. So you just assume you have this secure black box that you can send your input to and get back an output. Now build a security application, right? So you were building an application for, I don't know, whatever it is, whatever your application happens to be, whether it's a related to to health or finance or security. It doesn't matter what the application is. And you can just think about, you can abstract out this MPC component as a secure black box. And then as long as your application is secure using this black box, then once you replace the black box with an interactive MPC protocol, you know that everything remains the same. So that's really, really helpful for security professionals or computer scientists and software engineers who don't know MPC, are not cryptographers. If you're given an MPC protocol that suits your needs, that's also a challenge, right? Building the MPC protocol still needs to be done. But if you're given that, then you know how to use it, and that's important to understand. A couple of words of warning. Firstly, MPC talks about the process of computation, but not the function itself. So MPC tells you that nothing is learned by any of the parties, by any adversarial coalition. Nothing is learned except the result of the function. But so the process reveals nothing. You only get the output. But it doesn't mean that the output itself is okay to reveal. For example, if Rand and I run a secure computation to learn the average of our two salaries, then I know Rand's salary, because if I know my salary and I know the average, I can compute Rand's salary. And that means that this as a function reveals all the input. It's not an interesting function to compute, right? So in some cases, you have to analyze, if you're using MPC to do statistics, are the statistics that we're revealing okay? And if they're not, or if there's a concern, then you need to use other tools like differential privacy, but that can be actually combined. So MPC combined with differential privacy actually can have a lot of advantages in terms of the noise you introduce. So if there are questions about the function, that has to be dealt with independently. MPC doesn't talk about whether the output itself is valid to reveal or not. It just reveals the output, and that's important to know. So average of size is a problem, but if you're doing MPC of cryptographic functions, so one party has the key and the other input, or the key is split, then by definition, the output of the cryptographic function doesn't reveal anything that it shouldn't, because that's what the cryptographic function is supposed to do. So there are cases where it's very easy to understand that it's okay, and there are cases where it's easy to understand that it's not okay, and then there's the whole middle area that you have to really analyze with your application. In many cases, what people will say is, you know what, I have to compute this output, and it's either I do it privately or not privately. So in any case, I'm improving the situation, so we're okay. Is that legitimate or not? I think that's more for the privacy researchers and philosophers than it is for me to say. The second word of warning, as I mentioned, is that parties can choose their own inputs. And if it's a problem, you need to work that out into the definition. So if, for example, parties are inputting their salaries, and we think that somebody can skew it by putting in an incorrect salary, and we want to prevent that, then we should somehow get a signed salary and verify signatures or something like that within the MPC protocol. Sometimes that's easy, and sometimes it's not. Again, with in many cases, you can do a game theoretic analysis where you say, it's okay to change. If someone changes their input, that's actually not going to be in their interest because they won't get the utilities. So we accept that risk. Okay, so how does MPC work? We'll start with a fun problem. We have a guy and a girl, and they want to check if they're interested in going out. Okay, so it's the problem is that they're embarrassed to ask each other. The one is if I ask a girl out and she says no, then afterwards I'm embarrassed to see her. And if I'm in a work situation, it's even worse because I have to come into work the next day and she's next to me and I'm worried that I'm going to be embarrassed. So I think that a while ago I saw that Slack, there was some Slack plugin that someone had built that you could say if you liked someone in the organization, you could send that, and if that other person said you, then you would both get messages, hey, you two like each other. That's done without MPC, and so that information sits somewhere. I'm not sure that's a very good idea. But let's run it by MPC. So let's assume that everyone in class is going to pairwise check if they both say yes, then they get told yes. And if at least one of them is not, then the output is no. Now, it might be confusing, if I said yes and someone else said no. So I'm asking Nigel, I'm doing this with Nigel, and I say yes, I want to go on a date with Nigel. Nigel says no. You might think, okay, but I know that I said yes, and so therefore I know that Nigel said no. So what privacy has been preserved? The answer is that Nigel doesn't know that I said yes, right? Nigel sees no, and he thinks, okay, Yehuda probably also said no. So we both said no. I don't lose any face with Nigel on this. So here's the way we can do this with cards. Alice and Bob each get 2 cards, a king and an ace. And if Alice, this won't make sense to the end, so just bear with me. So if Alice likes Bob, she puts the king first and the ace afterwards. And if not, she puts the ace first and the king afterwards. And Bob does the exact reverse. So if he likes Alice, he puts ace then king, and otherwise king then ace. Then they put their cards on the table face down. So Alice can't see what the order that Bob put, and Bob can't see the order that Alice put. And they put an ace in the middle. Okay? Now let's have a look at the possible configurations. If Alice and Bob like each other, then Alice likes Bob, so it's king ace. And Bob likes Alice, so it's ace king. That means we have 3 aces in a row. But in any other situation, if either they both don't like each other or one doesn't like the other, we have these other 3 configurations that you can see. And if you look at all of these 3 configurations, they're actually identical up to a rotate. So they all have ace, king, 2 aces, and a king. Just up to a rotate. So the last one, which is ace, king, ace, those 2 aces at the end are actually next to each other if you rotate the cards. And so what they actually do, the parties turn over that middle ace and then randomly rotate. So Alice takes the 5 cards and randomly cuts, and Bob does the same thing, and then they open it up, and they see that if they have the 3 aces in a row up to rotation, then they both said yes, they go out on a date. And if they don't, then they have no idea, if they both said no or one said no, that remains completely private. For the computer scientists amongst us, what we've actually done here is compute an AND gate. And that's a sign we know that we can build any, compute any function from an AND and XOR gate, for example. So here you can do an AND gate with cards, and you can compose AND gates. So that will give a hint to what we're going to do later on. Okay, so in the 80s and 90s, there were a lot of very powerful feasibility theorems proven for MPC, which basically say that you can actually compute any function that you want. So for any number of parties, any function that's obviously can be computed in polynomial time, you can also compute an MPC. So we could, in theory, run SQL queries on a database that's encrypted, or say database that's split, or data that is split amongst multiple parties. We can do that without ever bringing the data together. And this could be, it doesn't matter what the size of the database is. Of course, it doesn't mean that it's very efficient, and we'll get to that later on. But in theory, it can be done, and we'll talk later about how it can be done efficiently. And the question is, how can you make a theorem? How can you prove an argument that you can securely compute anything? Anything means anything. Well, that's the advantage of the foundations of theoretical computer science. We know that we can represent any function as a Boolean or arithmetic circuit. So we have different basic gates, and then we can show how we can compute any circuit like that in MPC. And that means that we can argue that you can compute anything. And this will be very important, so we'll come back to it later on. It might sound this can never be even remotely efficient, but I'll come back to that as well later on. So I want to talk about a specific construction called Gauss-Gabel circuits. And it's probably the most technical part of what we're going to talk about, but it actually is, if you bear with me, you'll see that it makes sense, and it doesn't require anything too overwhelming. So we take an AND gate with input y is UV and output y is W. So what does the AND gate does? It maps pairs of bits to an output. So 0, 0, 0, 1, and 1, 0 all go to 0. But if both of the inputs are 1, then we get 1 in the output. And this is a single Boolean gate. And we want to show how we can somehow encrypt that gate and yet still be able to compute it. Okay? So the first thing that I do is I replace the zeros and the ones with random values that represent 0 and 1. Okay, so the U wire, I choose KU0 and KU1, which is two random values, two random cryptographic keys, for example, 128 bits long. And then I write, instead of 0 value, I write KU0, and the 1 at KU1. I do the same for V and W. So you can see that this is exactly the same as an AND gate, but instead of writing 0 and 1, I'm just writing these long random values instead. Now, if I would randomly permute the rows in this table, I would argue you would still know what the values are. And the reason why you would know the values is because in the third column, the value KW0 appears 3 times. And that means that you know that that is the 0 value, whereas KW1 is the 1 value, because you know it's an AND gate. And once you know what's the 0 and the 1, you would know also in the U and the V. So I couldn't give this table to someone and say, here's a garbled gate that you don't know, what the 0 and 1 values are. But what I could do instead is I could doubly encrypt each value. So I can take KW0 and doubly encrypt it under KV0 and KU0. And likewise under KV1 and KU0 and KU1 and KV0. And I could encrypt the 1 value for the W under KU1 and KV1. And then I could permute these in random order. And if I give you these 4 ciphertexts in random order, you actually know nothing, because these are just encryptions. You don't know which value appears more or less, because you just see ciphertext. So it's all hidden. But the important thing is, if I was to give you 1 key on each input wire, and I'll demonstrate this next in the next slides, it'll make more sense. But if I was to give you 1 key on each input wire, so I give you KU0 and KV1, you could try to decrypt the first ciphertext and you'd fail, because you don't have KV0. You would try to encrypt the second ciphertext, well, you would succeed and you'd get KW0 back. But you actually don't know at all what you've computed, because I gave you 2 random values, and you managed to get a 3rd random value by decrypting, but you actually don't know what you did. So you obliviously computed this AND gate without knowing at all what you've computed. And that's the really powerful notion of garbling a circuit. And these keys on these input wires, we call them garbled inputs as well. So let's see what we can do, how we can build that into something, a bigger picture. So I've taken a circuit now with 2 AND gates and 1 OR gate. And the first thing I do is I randomly assign a pair of values. I assign a pair of random values, to each wire in the circuit. Okay, so each circuit here, this wire is the A wire. I assign KA0 and KA1 and so forth, so on and so forth for all of the wires in the circuit. And then I just build the table from the previous slide for each of these gates. Okay, so the first AND gate, I just build exactly these 4 encryptions, where I'm encrypting the E values, because they're the output wires, with the 2 input wires, exactly as we saw on the previous slide. And then I do the same thing for this AND gate. I'm encrypting the F random values with the A and the E ones. It's exactly the same. That's over here. And then finally, for the OR gate, I do the same thing. I'm encrypting the G random values using the E and the D. Here it's an OR gate, so notice that KG1 appears 3 times because it's an OR gate and not an AND gate. Okay, so I can now give you these 3 garbled gates, these 3 tables that essentially are encryptions of each gate. And I also give you what we call an output translation table. So give you something that enables you to go from the random values at the end to the real values. So here I tell you, okay, if you've got, sorry, excuse me. Apologies. So if you get KF0 in output, you'll be able to look at this pair here and know that that actually means 0, because somehow you need to get the real output in the end. Okay, so this is a garbled circuit, and now I want to show you how you can actually use this to compute. So let's say I have input 0101, and I want to give it to somebody else to compute this circuit without knowing anything that they've done except for the output. Okay, so this is the input. I give them the garbled circuit, which is the 3 tables for the gates and the 2 output translation tables. And then I also give them garbled values on the input wires. I give them KA0, KB1, KC0, and KD1. Okay, so I give them these values, and I have these encryptions. Okay, and we don't need to go into the exact definition of the encryption. The encryption, just think of it as a black box for now. It really works in this way, in this construction. And so they have these values, and what they can now do is go gate by gate and compute. So the first gate in the topological order of the circuit is this AND gate. So they have KB1 and KC0, and they can go to the first table and they find that it decrypts the 3rd row. Of course, as I mentioned, these are all in permuted order, so the order doesn't reveal anything, but for the sake of this demonstration, I'm leaving them in the correct order. So they go and they manage to decrypt this 3rd value, and once they do that, they now have K0E as the result, which makes sense because they had a 1 and 0 on the input. So they get K0E. The next, they can now go ahead and compute the next AND gate using A and E, so this AND gate over here. And how do they do that? In the same way, they can take KA0 and KE0, and they find that they decrypt this first ciphertext, and they get KF0 as output. Finally, they can go to the 3rd gate, the OR gate. They have K0E and KD1. They find that that decrypts the 2nd value, which gives them K1G. And then they can now finally take K0F and K1G and look at the output translation table and see that they have 0 on 1 for output. Okay, so they'll learn that the output is 0, 1. And what I'm going to argue now is that there could actually be multiple inputs for this, because it could be 0, 1, 0, 1, but it could also be 1, 0, 0, 1 would give the same output, as would 1, 1, 0, 1 would give the same output. Or 0, 1, 1, 1 would give the same output. In fact, there are many different outputs. So there are very many different inputs that give the same output. And you computed this circuit, you got the output, you didn't learn anything else. And that's exactly what we want in MPC. Okay, so I hope that makes sense, made sense. That's the most technical part of the talk. So I hope it made sense to everybody. But now I want to build from that an actual MPC protocol with multiple parties. So I want to show you a 3-party protocol that is secure as long as at most one of them is corrupted, is a malicious party. They can try to cheat however they want. Okay, so party P1 is this server over here, has input X. Party P2 is this server over here, has input Y. And party P3 has no input. We call them an auxiliary party. They're there to help. Okay, and it's going to be secure as long as at most one is malicious. So nobody has to trust anybody else, but we're assuming that no two will collude together. Okay, as long as that doesn't happen, this is exactly the honest majority setting we talked about. So how does this work? The first thing, this garbled circuit needs a lot of randomness. So the 2 parties choose a seed for a pseudorandom generator, basically generate a lot of randomness. So they can both build the same garbled circuit because it's just randomness. So if they have the same random seed, they'll generate the same garbled circuit. And then the first party will generate the garbled input that relates to his value, because that's just choosing, you know, is it KA0 or KA1? Is it KB0 or KB1, depending on the bits of X? And the second server does the same thing for Y, and they send all of this to this 3rd server here. So this 3rd server, the 3rd party, receives the garbled circuit from both and the garbled input related to the respective inputs. The reason why we send both the garbled circuit from both is because one real problem when using garbled circuits is that because it's encrypted, you actually have no idea what function it computes. So you might think you're computing one function, but really compute something else. And that would be a huge problem. But if both P1 and P2 are sending the garbled circuit, then P3 just checks it's the same. And if it's the same, then it knows that at least one of P1 and P2 are honest, and that means that it knows it's the correct garbled circuit. So the other party who's corrupted cannot send anything but the valid garbled circuit, or else it will be detected. Once this third party has the garbled circuit, verifies that they're the same, they have the inputs in exactly the same way as we showed on the previous slide. They're able to compute the garbled circuit and get the output and send it back. And they can send it back in a way so they can't change the output either. So this is an MPC protocol for 3 parties. It's secure against malicious adversary corrupting one party because nobody can do anything that they're not allowed to do by the validation of the garbled circuit. And the third party just has encrypted values, can't do anything except to compute the circuit. It can't change anything because it doesn't know anything else to do. And we can, of course, prove that formally, but just take my word for it for now. Now, I just want to stress this is a simple protocol. There exists also protocols for 2 parties that secure against one corrupted. There are protocols against that can involve many parties and will be secure even if a dishonest majority, if there's a dishonest majority. But this is the protocol that I'll show here. Okay, so that's it. That's doing for general secure computation. What about specific tasks? Because sometimes we can use certain properties. That protocol talked about something very generic, which is, MPC of a circuit. So it can be used to represent any function. I'll show you later on that that's really important in practice. But sometimes we also have very specific tasks we want to solve, and then we can do different things. The first thing I want to talk about is threshold cryptography, which is to compute a cryptographic function without any single party holding the key. So I'm going to split a key amongst parties and require them all to agree in order to carry out the operation. Why would I want to do that? Number one, I'm going to make it hard to steal the key because the key isn't sitting in any single place that I can breach and go and steal it. And the second thing is I would like to maybe, for very sensitive operations, require a quorum to authorize it. Signing on bank transactions, or more recently, if you followed the SolarWinds, the massive SolarWinds saga, what happened there is the attackers managed to get a legitimate signature for a code signing key on malware that they then pushed out as a software update, and were able to go and breach thousands of networks and organizations and US government organizations. A huge breach, but it was caused by managing to use a key maliciously. But if in order to sign on code, you would need a quorum of parties to agree to it, and they would know that, they would verify that indeed there is an update and what the update is and so on and so forth. You would very much mitigate that sort of attack. Okay, so how can we do this? Let's look at RSA. Okay, so the RSA function, and it doesn't matter if you're familiar or not familiar, all you need to know is that the RSA private operation for signing or decryption is taking a value y, which is derived from a message or a ciphertext, and raising it to the power of d, where d is a secret value. Now, there is also mod n, and but you can just ignore all of the modular operations, what I'm going to talk about now. So the secret operation is y to the power of d, and this value d is the secret that we want to protect. So first, I can just share this simply between 2 parties, 2 servers, S1 and S2, by choosing D1 and D2 at random, so they sum to D. Okay, so S1 can choose a random D1, and S2 just sets it to be D minus D1. Again, I'm ignoring the mod. You can just ignore all the mod. So we have D1 and D2, so the D1 plus D2 equals D. And the important thing is that if all you have is D1, that's server S1, then it reveals nothing about D because it's just random. And D2 also reveals nothing about D because D1 actually completely hides D. Okay, so see, S2 has D minus D1. It's like a one-time pad, right? D2 actually, if you're just given D2, you know nothing. So neither S1 or S2 knows anything about the secret key D. So recall that S1 has D1, S2 has D2, and they sum to D. And they want to compute this private operation of y to the power of D. And they need to do that without anybody learning anything about D itself. This seems to be difficult, but actually it's very easy because raising to the power of something has a very nice algebraic property. So S2 just computes y to the power of D2 and sends it to S1. S1 computes y to the power of D1, so they only do local operations, and then S1 can multiply these together. And the algebraic operation that we're looking at is when you multiply two values together that were computed by raising the same base to different exponents, you just add the exponent. Okay, so Z1 times Z2 is y to the D1 times y to the D2, which is just y to the power of D1 plus D2. And that equals y to the power of D. Okay, so in the end, they get the result, but they didn't reveal anything about D1 or D2 to each other. And also by S1 verifying, there's a way of, RSA, is an invertible function, so you can actually compute back and check you got the correct thing. But I don't want to go into all those details. Now we can prove formally that this reveals nothing beyond the result. But again, intuitively, you can understand why, because D1 and D2 are never revealed to each other. And then you can build a protocol from this for, type of, doing RSA operations without keeping the key in any single place it can be stolen. Maybe you want to do this for TLS, or you want to do this for code signing. So a client will send a hash message as part of a code signing operation, for example, and they'll just run this protocol. The second server will compute y to the power of D2, send back to the first server. The first server will compute y to the D1 and multiply together and send back the result. So this could give you like a software type of HSM, hardware security module that can run in the cloud or between environments, so that the key is never in any place to be stolen. And that gives you a very, very simple MPC protocol. But there's something also called proactive security. And proactive security is a notion in MPC which tells you that I'm concerned that, so you split this key D into two places, but maybe I'll corrupt one machine today and it'll take me 2 months to get to the other machine, but I'll get there eventually, and then I'll steal that part. And then eventually I'll have D1 and D2 and I can add them together. So what we can actually do is we change the sharing so that the attacker has to essentially breach both machines at the same time, in the same interval, for example, in the same hour. So how do we do that? The servers run a coin tossing protocol to get a random value R. That's a very simple MPC protocol. I won't go into how they do that, but they get a random value R that neither can influence. And the first party just adds R to their share. The second party subtracts R from their share. And obviously D1 prime plus D2 prime equals D, because you just added R and subtracted R, so it cancels out. But if an attacker steals D1, because they broke into the first machine, and 2 hours later, when they're no longer on the first machine, they're in the second machine and they get D2 prime, then all they get is D1 and D2 prime, and that reveals nothing whatsoever about D, because that value R, again, hides, is like a one-time pattern, hides the value of the secret key. So this notion of proactive security is a very powerful one. It means you can have these long-lived MPC systems where the keys are, or where the secrets in general are protected on an ongoing basis. It's possible to do other threshold cryptography. You can do ECDH and ECDSA and Schnorr and EDDSA and key generation, and they mostly have nice algebraic structure, so we can build dedicated protocols. But there are a lot of cryptography which has no structure, like AES and HMAC, and what can you do in those circumstances, right? Because it's just strange, there's no structure at all. And the answer is that you can use the garbled circuits method that I showed you beforehand. There are other methods as well, but just as an example. And because they can compute any function, you can use it to compute these as well. So you can protect AES keys and HMAC keys in exactly the same way as what we do for RSA. And this but you might ask, okay, but this is going to be really expensive, right? AES has 31,000 gates, 6,400 AND gates and 25,000 XOR gates. There have been many, many optimizations. We can make XOR gates essentially free. We could do AND gates more efficiently than I showed you. So it can take, half a millisecond to garble and evaluate an AES circuit. And actually, just to understand, we can do on not powerful machines, on just this quite simple 4-core 10 gigabit machines in Azure, for example, we're going to do 500 AES GCM operations with AES 256 on a 32-bit input. So that's for like a key wrap operation. So this is a very important operation. And all of that, all the communication, generating these garbled circuits, evaluating them, sending back and forth, we get a throughput of 500 per second. So this really is efficient enough to use and achieves high performance. So that is important to know. Let's look at another concrete example, private set intersection. So we have Alice and Bob that have sets A and B, and I want to compute the intersection. For example, I join Signal, and I want to know who else here is on Signal. Wouldn't it be great if we did a set intersection protocol where we would see that I would be able to learn that Nigel, so Signal holds this list of contacts, and only those who in my contact list who are in their contact list I would learn about. So that means that Signal wouldn't learn people in my contact list who aren't Signal members, and I wouldn't learn anyone who's on Signal that's not in my list. Signal doesn't do a secure private intersection protocol. They use just simple hashing, and inside they use SGX, but that is not a secure MPC protocol. I won't go into why. The problem has many solutions, and there's been a lot of work done, and I'll show a very conceptually simple one here for semi-honest adversaries. And the tool that I'm going to use is something called oblivious pseudo-random function evaluation. And a pseudo-random function is just a function that, given input, outputs something which looks like random garbage and not connected to the input. And this tool is an MPC protocol where Alice inputs a key K for the function, Bob inputs in their value B, and Alice will learn nothing while Bob will learn the function on B with that key. Okay, so Bob will learn this pseudo-random output, which looks like complete garbage, and Alice will learn nothing. Concretely, this could be AES or a pseudo-random function based on elliptic curves. Let's just think for now that it's AES. So just like a block cipher, Alice has the key, Bob has the input, and Bob gets the output, and Alice learns nothing. So it's a type of basic encryption primitive. So Alice has this input, her input set A1 through AN. Bob has his input set of B1 through to BM, and they want to compute the intersection. The first step is for Alice to choose a random key for this evaluation, and for them to run many executions of this oblivious AES evaluation. This, by the way, could be done using the same protocol that we used beforehand if there was a third party, or it could use a different protocol. It doesn't matter, but using some MPC protocol, they can run this where Alice inputs K, Bob inputs the input BI and gets back YI. And then Bob at the end will get, will have the outputs for all of his inputs, Y1 through YM. Alice will then locally compute the AES function on her inputs. Okay, so locally compute X1 through XM, which is AES on all of her A values, and we'll send them to Bob. And Bob will get this list X1 through XN, which are just AES encrypted values of A. So actually, Bob doesn't know anything about the A values, because by the security of AES and by the fact that Alice chose the random key and Bob knows nothing about it, he learns nothing about Alice's inputs. But what Bob can do is compare which values did he get that are in Alice's list. So Bob can look for values where YI appears in Alice's list. And if YI appears in Alice's list, that means that Bob's BI actually equals some AJ. In other words, it's a value in the intersection, and he can just know, oh, okay, YI is in Alice's list, so therefore I know that BI is in the intersection, and he can send back also, he can get output and send it back to Alice. This is only secure for semi-honest adversaries. You need to add more for malicious, but I think it really demonstrates that it can be done very simply and very efficiently. You can just run these computations. In the end, you can compute the intersection without revealing anything more, and I'll show you real-world uses of that in a moment. Okay, so to sum up, we've talked about what MPC is. We've talked about techniques, and now we'll talk about actually using this in practice. So anybody who lost me in the techniques, that's absolutely fine, because now we'll just talk about the use cases in practice today. And in practice, I mean in production. These are things that organizations are actually using. Okay, so advertising conversion for Google. So the problem that Google wants to solve is as follows. I get an advertisement to buy a BMW on my mobile phone. Don't worry, Google is smart enough not to show me any such advertisements. So, but you know, if I had a lot more money, maybe I would get advertisements to buy a BMW. And you know, when I'm looking at my newspaper on my phone, and the question is, how can Google determine, and BMW, how can they determine the effectiveness of that advertisement? All right, it's not like if I'm shown an advertisement for something that I can buy on my phone, then I'll see, okay, so Yehuda was showing this advertisement for a set of headphones, and he bought it online, and therefore we know we can correlate the fact that I was shown the advertisement to the fact that I actually bought that. But if it's a BMW, no one buys a BMW from the phone. I saw that advertisement, and then I went into the dealership, and that's completely not connected to the fact that I was shown the advertisement. So how can we do this? The solution is we can compute how many people were shown the ad on their cell phone. And we can compute how many people who were shown that ad actually bought a BMW. So if I could have the list of everybody's, the phone numbers of everybody's cell phone who was shown the ad, and I could look at the list of the phone number of everybody who bought a BMW, that's information that BMW has, and the first list is the information that Google has, then I can correlate and see the conversion percentage from being shown an ad to buying a BMW. You also want to normalize this by what's the expected, what would be the expected chance that I would buy a BMW if I wasn't shown the advertisement. But let's leave that normalization out. Now this is a classic, but the problem is that Google and BMW don't want to share their lists. This is a significant privacy concern. Well, the whole thing is a privacy concern in Google, but this is even bigger privacy concern is going outside of Google. And Google actually solves this by using private set intersection. They don't actually show the phone number of who appears. They use a variant of private set intersection, which just gives the cardinality or the sum of amounts spent. And Google actually uses this to truly measure the effectiveness of advertisements, and in that way preserves privacy while being able to know how much to charge for showing advertisements to for products like a BMW or something like that. Okay, that's a real product in production used by Google. Another interesting use case was done in Boston. This isn't a commercial use case, but it's a what we call MPC for social good. The Boston Women's Women's Work Council wanted to run a study on the wage gap study. So they wanted the wage gap between men and women in different organizations and companies in Boston. They went to the companies and asked, can you give us information? And of course they said, no, it's private information. They were probably also worried about the fact that they could be legally in trouble if they're worse than others. And what they actually did is they managed to build this in conjunction with Boston University. They would actually be running MPC. So they actually ran an MPC where the different organizations input information about their employees and whether they're male, female, and how much they earn. And they managed to get to a situation where they had over 100,000 employees in this study, and they could really work out what the wage gap truly was in Boston. So this is a large scale. Here we're talking, in 2018, there are 125 employers, 140,000 employees in the study, $12 billion in annual wages, and they could see the wage gap between men and women at scale that previously was impossible to actually compute. And you can look up the Boston wage gap study, you'll find a lot of information. Here's how they're explaining how it's done. And so this is a very interesting use of MPC for social good, and there's been other work on that, which is really exciting in my opinion. Duality is a startup company that is using a mixture of MPC and fully homomorphic encryption. So it's also a type of MPC that in order to enable different organizations to really share data, or at least compute analytics on shared data. it's important, I want to stress that the main difference, again, between MPC and fully homomorphic encryption is interaction. So where you can interact, essentially, there's no reason not to use MPC. But there are use cases where fully homomorphic encryption is great because you can just outsource the computation to someone else and just get the result and decrypt. That's something that you can't necessarily do with MPC. With the MPC, you actually need interaction, but the state of the art of MPC today is that it's orders of magnitude faster than fully homomorphic encryption for the vast majority of use cases. I'm not saying that there aren't cases where it changes, but typically that's the case. ShareMind, similar model to allow organizations to collaborate, to compute, for example, Estonia wanted to correlate tax records with education records to understand, do students that go out to work, are they contributing to the fact that more students are failing? So I did this computation, and the result was no, the fact that students are going out to work while they're studying is not contributing to their failing. Although with my professor hat on from my past, I think students should focus on their studies and go to work later, but that's completely not related to MPC. And finally, for key protection, I mentioned this beforehand. This is what Unbound does. So again, splitting keys into 2 or more pieces, using them without ever bringing them together and continually refreshing them. You can have this actually deployment is a real deployment of a large bank in Europe that's a customer of Unbound. They're splitting the keys between 3 pairs of machines. EP and P is entry point and partner. So that's the pair of parties running an MPC computation on keys. And they had 1 pair between their on-premise data center and AWS, a second between AWS and Azure, and a third between Azure and their on-prem data center. So there are application servers in AWS, Azure, and in their data center that can all access what we call the entry point, so they can do the computations. And but the key is not holding any place because each pair holds an independent sharing of the key. An attacker would have to simultaneously breach 2 completely different environments in order to learn anything. Again, that's a real deployment in production today. I talked about the SolarWinds beforehand and this notion of a quorum authorization. And here's where MPC can move beyond key theft, which is just preventing someone from stealing a key, to actually preventing someone from misusing the key. Okay, and you can do this by setting up, a quorum. So you would need 2 out of 3 parties from the R&D team and 1 out of 2 parties from the legal team in order to sign on code that we pushed out. And the cryptographic key for signing would be split between servers and even maybe these people's mobiles, and they would all participate in MPC protocol to ensure that that cannot be bypassed. Even an attacker got into the system without breaching a full quorum that is able to authorize, they wouldn't be able to get that code signed, and that's a powerful paradigm for protecting cryptographic infrastructure. Another use case of that is you could do 2-factor authentication with MPC. So you'd like to use your mobile because you carry it everywhere and it can do operations, but it's extremely vulnerable. It's very insecure. But you can build a virtual smart card or one-time password token by sharing the key between the mobile and the server and having the key never on the mobile to be stolen. Again, refreshing so that gives you strong anti-cloning. You have auditing. There are a lot of advantages to this model. It's very easy to deploy and manage. And again, the fact that the key isn't actually resident on the mobile means that you can get strong protection while using a mobile. And this is actually also used by this is in production. Millions of people are actually accessing their mobile app for their bank via this without knowing it. It's completely invisible to them. So in summary, MPC is a mature technology, one that's ready for deployment. It still requires high expertise to deploy. So you need to understand what problems you can solve efficiently. You need to tailor protocols to specific needs in some cases. There are subtleties in published protocols. So a lot of papers on MPC will talk about things, but they won't necessarily say verify that this point that you get is indeed on the elliptic curve, but you have to do that. So there are a lot of things you need to still understand in order to do that transition, but there are more and more people out there with that expertise making this a reality. And it's being used in production, and it's getting more and more exposure. And as we get that exposure, we're learning from the market what problems they want solved, and indeed its use and interest in it are actually growing very, very fast. So thank you very much, and I'll be happy to take any questions.
Okay, great. That was fantastic. Thank you very much. That was really, really good. Great. So we've got a first question from Jan.
Right. So seems I can't share my video anyway. Thanks for the great presentation. I have a question regarding kind of how to prove that I participated in such an MPC protocol. So for instance, I know my input, and after the protocol is run, I also have the output. How can I kind of show an independent party that actually this output originated from my input, even without kind of sharing everything, and also trying to, in the best way to keep my input still private? Is there a way to do that?
Yeah, so obviously you know that it's correct because you participate in the protocol. And if it's secure against malicious adversaries, then you have that guarantee. Once you want to show to someone else, there are two possible things to do. One is to define that as part of the function that you're computing. So you could define a function where the result is the output signed with something along with the, I don't know, the identity of all of the participants, with a signature key, with a signing key that is shared amongst all the participants, and the public key is a published one. If that works for your scenario, that's one possibility. The second is defining a model which enables you to come out with, again, assigned audits of the computation. There has been some research on that in what's called the setting of covert adversaries. A covert adversary is an adversary that can cheat like a malicious adversary, but there's a guarantee they'll be caught. And there's been work on how do I make sure that if someone is caught, I can actually get also proof that they were cheating, so I could show to someone else, and therefore there'll be some punishment of some kind. So there has been work in that area. There's no straight answer to your question. Rather, I would say there certainly are techniques out there. What you would need to do is define exactly what the setting is, what sort of computation you're looking at, whether this idea of sharing a key in a generic way would work or not. And if it does, then how can you build an efficient MPC protocol for it? Or, there's a lot of very interesting MPC research still out to be done there. So defining such a model and seeing, can you do that in general, and how efficiently, that would be an interesting research question.
All right, thanks for your input.
Great. Cohen, I'm not sure if that's how you pronounce your name. Let me unmute you. If you guys,
it's about right.
If you can put your video,
yeah,
that'd be great. It's more fun.
I can't start my own video.
You can't.
I'm not allowed
to. Allow participants to start video. There you go.
Nice. Okay.
Yeah.
Hi.
Hey, thanks for the presentation. First of all, really great, very interesting. So earlier in your presentation, you mentioned that when using MPC, nothing is learned except for the output of the function. But if that output is also sensitive information, we could combine it with differential privacy. If we would do that, we would make that combination. How would we go about adding the noise of the differential privacy? I think you should do it before you reveal the output of the MPC function, since that is private information now. How would it work conceptually? Would that also be a joint computation in that case?
The way that the typical way of using differential privacy is if you wanted to do differential privacy on many people have inputs, you want to compute statistics, is you would tell each party to add noise to their own input, and then you would just reveal it and do a computation. The problem is you then have to add a lot of noise because each party has to add noise, and there's a lot of noise and you lose a lot of utility. But what you can do with MPC is you would define the function, again, thinking about this ideal model paradigm and this secure, we have this trusted party, you would define the function so that it would compute the statistic and only add noise on the aggregate at the end. So rather than computing the mean and standard deviation by taking noisy inputs and computing upon them and then getting a lot of noise, you would inside the MPC compute the mean and standard deviation and sample noise for differential privacy and add it, and only that would be the output of the function that would be revealed. So nothing intermediate is revealed because that's you define the function that computes it all together, and you are now only have to add very little noise at the end. And how much noise that is, I'm not a differential privacy expert, so you will have to work with, bring those forces together. But you can add much less noise and get much greater utility by combining the two together. Does that make sense?
I couldn't unmute myself, so sorry about that. Yeah, would it be more costly to do when you include it within the protocol?
So that depends.
So for some things like secure aggregation, that's fairly cheap. But if you would just compute a mean, for instance, but then when you add this to the protocol, would it become much more expensive? So
it will certainly become more expensive because you're adding an operation. But if you're using generic MPC, then it probably won't add a lot. If you have something which has a very dedicated you have a dedicated solution for, then it can be tricky. But this is something that one would have to research and look at. My intuition says that there are many cases where you won't be paying a severe penalty, but there are others where it would be more. And it also depends on, there's different differential privacy sampling as well, and some sampling is easier than other, right? So how efficient is it to sample a Gaussian in MPC?
Okay.
And that's part of the research that needs to be done, but I think that in many cases can be done. A lot of these also, especially these type of statistics use cases, we don't need real-time solutions, right? So if it's a little bit more expensive, it's okay.
Okay, thank you very much.
Rand, you're on mute as well, but we saw we read your lips that you said Daniel, so Daniel, go ahead.
Oh, great.
Hi, so I have a few small questions regarding the garbage secrets and the protocols that you showed. So you showed a basic protocol for 3 participants. And I wonder, first thing, how does the 2 first participants know that the output of the auxiliary participant is correct and is not malicious? That's the first question. And the second question about that is that you assume there that the communication is not compromised because they share the seed. And are there any protocols or other settings where you can remove that assumption?
Yeah. Okay. So for the first question, when you look at when you think about the gobble circuit operation, at the end you get these wires you get these random values on the output wire. So in the small example we showed, there was like K0F or K1G or something like that. I don't remember. Okay, so you had those. So because everything is encrypted, that is the only value that the auxiliary server sees. And if the auxiliary server doesn't send back 0, but sends you K0F, then they're unable to come up with K1F because it was all encrypted. So they can only learn one of the random values on the output wire, and therefore that proves the actual value that was received. So this is also proven in there's literature on generics of garbled circuits, and this is actually a proven property that you get from garbled circuits. So that's easy. In terms of the secure channels, so firstly, in practice, we assume secure channels. You can assume that, at least in the Unbound setting, that these are servers that are set up and you have TLS channels, or it's in a mobile and a server, you can set up a mutually authenticated TLS channel. So therefore, we can assume secure channels. In general, in protocols that assume an honest majority, you typically have to have a secure channel. So if you can't assume it, but if you then you have a problem. If you have a two-party protocol, and where it's secure against only one being corrupted, in principle, there's not much an attacker can do. Eavesdropping certainly will reveal nothing, and even in an active attack, you can argue certain properties. But in reality, in practice, setting up secure channels is not a concern.
Okay, thanks. And I have another small question, something I didn't understand about how garbled circuits work. At the end, you said that you need to, so all of the outputs are encrypted, and you need to try to decrypt every row in the table until you succeed to decrypt one of them. And that's how you know what is the output of your two inputs, right?
So that's the way I presented it. In practice, so we don't do that. We have better solutions for that. So, the original garbled circuit, you could do that and have some redundancy so you would know if something decrypted correctly or incorrectly, or you could use authenticated encryption so you would know if it's encrypted correctly or incorrectly. But there are, what I showed is conceptually the way it works. Today, after many, many years of research, there are much, much more efficient ways of doing that. We know exactly which one to decrypt. Not only that, we can reduce. We actually don't need 2 ciphertexts and not 4. So there have been a lot of optimizations. What I showed you is the conceptual notion, and there's a lot of literature to read to understand how garbled circuits.
I was just wondering, how do you know when you were successful in decrypting?
Yeah, so if you wanted to think about using authenticated encryption, then you would have a MAC that would fail. In practice, we don't do that, but conceptually, such a thing is possible.
You have a what? Sorry, I missed your last sentence.
A MAC, a message authentication code. Authenticated encryption is something that, if it's incorrect, it would fail. So you could use something like that.
Okay, thanks.
Pascal, you have a question?
Yes. Yes, hi. Hi, Yehuda. Thank you for your super interesting talk. I don't have really questions about the crypto side of things, more about, I would say, the perception of MPC in the industry and how globally it can be adopted, or if you're like, with your experience at Unbound, what kind of experience do you have in terms of deployment? I mean, are people, I mean, what are the roadblocks for general adoption of MPC?
Yeah.
And maybe you can talk as well of your experience with certification. I believe you went through a FIPS 140-2 certification at some point, which must have been a nightmare. Probably nobody.
Yeah, but I have a nice story around it.
Nobody probably in the certification space had actually evaluated a full-fledged MPC solution before. Can you talk about that?
Absolutely. So I'll start with the first question around adoption and barriers and awareness. So when we started 5 years ago, what's MPC? What is that? That's not possible. You must be talking garbage. But we've come a long way since then. MPC as a technology has appeared in what they're called 5 Gartner hype cycles, which is certainly new technologies coming to the market. A lot of people have heard about MPC. We get this "what is that" sort of question much less today, if at all.
Mm-hmm.
In terms of adoption, we have 3 of the 5 largest banks in North America using our product. We have about 10 banks overall as our customers, and we have other very, very large non-financial, like one of the largest software companies in the world, use their product to do all of their code signing globally.
Mm.
So there is, we're at the point where we see that there is enough adoption that the market is willing to do it, is receptive to it. They understand the value of having a software solution. The HSMs are both a pain in the butt. They don't necessarily provide the security they claim as well. And when you want to be multi-cloud and hybrid cloud and have everything else is virtualized, you need software solutions.
Right.
So there is more of that awareness. Having said that, we still have work to do, right? We still have a lot of work to do. It's not that, but it's certainly in production at very conservative organizations. And we're able to get over that. We're over that situation where people sort of look at you strange or what are you talking about? Mm. Having said that, there are certainly organizations that say, listen, I've been using hardware for 30 years. I'm comfortable using that and I don't, so there's certainly both, but adoption is, I don't think that we're losing contracts anymore because, oh, it's MPC and I don't know what that is. There are lots of reasons why someone wants to buy, another HSM from Thales, or they want to use the cloud KMS for their solution. And there are a lot of, there are different trade-offs. I'm used to this solution. I had it in the past, but we're getting less that, okay, this is a strange new technology I don't understand. I'm not saying it doesn't happen, but it's happening less. In terms of, I hope that answers the first question. In terms of certification, so yeah, I spent a long time working with NIST, and it wasn't easy. And in fact, there was even a real barrier in that the FIP specification talks about a single boundary. And we wanted to argue that if an MPC is not in a single boundary, right? So if I could have easily certified by running both sides of the MPC on a single machine, and I would have FIP certification for that. But we don't have FIP certification for whether you really run it in practice, which is on different machines. Right. So we argued to NIST that if you take our modules and you run them on different machines, but connected with a FIP certified TLS channel, you should define that as a single boundary. Mm. And I actually did a workshop at NIST. I went out to Virginia and I did a workshop for half a day on MPC. Both their research group, which they have serious cryptographers in the research group, probably know them, and also the CMVP, I think is the group. They came and we presented what is MPC about. They understood that not certifying this, which is much more secure than standard software, is crazy. And eventually they had to do some work to allow this definition of two separate modules with a TLS channel. And we got both level 1 and level 2 certification. Level 3 and 4 we cannot get because it explicitly requires hardware protection. So by definition, we can't, it doesn't say if you have hardware then, right? That would be fine. It says the hardware has to be this. Yeah. So we can't do level 3 and 4, and NIST is actually running a threshold cryptography process, but it's, if it happens in less than a decade, I'll be surprised. But my hope, and this is one thing that I said to them, is that if you only enable us to get level 1 and level 2 with this, then there's no point. You have to think about a process that will allow us to get at least to the same level of hardware, because it's a different security paradigm, but one that is certainly just as valid as hardware, and I would argue actually more valid in today's environment. When you look at the HSMs, you have no idea what's running inside there, and they're completely opaque.
Right. I'm not sure it would have been easier to go for a common criteria certification, right?
So with common criteria, the easier part about common criteria is that you define there a certain, what's the term?
Target of evaluation?
Yeah, the target evaluation, but then there's a profile, right? You define a certain profile, and then you can make that profile suited to what you're doing.
Right, exactly.
And then, but the question would then remain, if a bank, because what did banks do? Level 3 and 4 regulation is not mandated. This is internal bank regulation. But what they did 25 years ago, they said, okay, we need an HSM. There is no other solution. The good HSMs are level 3 and 4, so we require level 3. But there's no real reason for that. So either the bank decides that they can get over that, and certainly some already have, or they say no. That's. But if they're using common criteria, if they've put hardware inside their profiles that they require, then you haven't really done very much. And common criteria is very expensive and even longer than FIPS. So
it is.
Yeah. So, but it is an interesting question that we think about every now and then.
So, don't you think it would be worth the pain of going? I mean, of issuing a protection profile specifically for MPC to kind of pave the way to further, certifications for MPC. I mean, it could be, I guess, once it's done, people now have a referential to apply the CC methodology, and then it could benefit the whole ecosystem. Have you considered like doing that or getting some help?
I think that is actually a very good idea. We did look at starting common criteria. The price that was at that time was so high that we felt we needed to wait.
Yeah.
I'm not sure it's something that we'll do this year or right now, but actually, given this conversation, I think it's something that I think we should put more thought into, and I think it does make sense. So exactly when I'm not sure, but I think your approach is very valid, and we should consider it.
Interesting. Okay, thanks very much.
Thank you.
Do we have any other questions? Guys, just raise your hand if you have any questions. If not, I actually have one. I was wondering about whether MPC was prone to some kind of side channel attacks, and if so, how serious are they? How difficult are they?
Okay, so the first thing I'll note is that a timing attack would certainly be one that you need to think about, because if I'm doing RSA between two parties, so I've corrupted this machine. If I can time the response time from the other machine, then I can corrupt one machine only and learn. So timing attacks, certainly you need to think about. For example, so we use OpenSSL for most of the underlying basic crypto operations. And when we're doing the RSA protocol that I showed you in the slides, we make sure that we use the constant time exponentiation.
Okay.
So that's certainly time you need to think about. What about the other things? So with other things, there are two answers that I'll give. The first answer is that according to the security model we talk about, if you corrupt only one machine, you can't learn anything. You need to corrupt both. Now, if you do a side channel attack, therefore one machine, you certainly can't get anything. So the question is, okay, so what do we say about side channels on two machines, right? So I managed to get on the same physical machine as two virtual machines running MPC. What can I do there? And the only answer I can tell you is that this is completely fresh, unresearched territory, and what's the word? It's
uncharted.
Uncharted territory, exactly. Intuitively, this is going to be a hard side channel attack because you need to look at things that are correlated between two different executions, essentially at the same time, and bring it together. But my gut tells me that absolutely such a thing would be possible. So the best practice is, of course, to limit with your operations. That's why we chose to use, for our low-level crypto, we use OpenSSL. Even when we needed to use, for one of our protocols, we used Payer. So we tricked OpenSSL into thinking Payer is RSA. We have a nice trick for doing that, by the way. We tricked OpenSSL into thinking that Payer is RSA, because now I know that the operations that I'm doing have all of the side channel sort of protections around that are built in for when you have a local, same thing with elliptic curve operations and so on and so forth. We're going to make sure that we're using the same low-level operations that are supposed to be side channel proof, because typically people are using them in isolation. But otherwise, yes, this I believe it's something that should be a concern. But by having this model, think about now breaching two different machines at the same time, having control and having a virtual machines on two at the same time, being able to run active side channel attacks and correlate that. everything's possible in the security world, right? And nothing's impossible, but that becomes, much harder and much less likely than, getting onto one machine and running that side channel attack on that.
So that would be like a nation state type of adversary that you would consider for something like that. Not
I think it would.
A group or something like that, right?
I would think so for sure. Yeah, and even then, so we're playing around with ideas of running the SGX. I don't trust. I think SGX is leaky. It just doesn't work. But it's great as a secondary measure, right? So what about running MPC inside a trusted enclave? Right? You're not still fully malicious MPC. I'm not trusting anything about this,
just
this SGX or other trusted execution environment, but you're making now a side channel attack. You need to run a full side channel attack. You can't get a snapshot of the memory, even if you're on both machines. So that's where it becomes of interest. Okay,
great. I think we don't have any additional questions. Do you have any last comments you want to make?
No, I enjoyed it. I hope that everybody found it beneficial, and the discussion at the end was great as well.
Can you share maybe the link to your company? Maybe if you want to share like your Twitter. I think.
Sure. It says chat disabled.
Let me enable that. Let's hope that the Zoom bomber left by now. All right, there you go. That should work.
So the company is Unbound Tech, and that's the URL. You can have a look. And my Twitter is just Yehuda Lindell.
Perfect. Well, thank you very much. That was really great. So guys, the idea is that for this meetup, every month we're gonna cover a topic around secure computation. Since this was our second meetup, the next one's probably gonna be also an introduction to another technique. If you've got ideas, please send them to me. And once we've gone through maybe 4, 5, 6 different techniques, we'll start digging super deep into way more technical stuff or way more like, example applications. Again, very happy that we now have 1,000 people in the group. That's super exciting. This group is 6 weeks old. So that's a pretty nice uptake, especially considering that we've only posted on Twitter. I think, a big part is thanks to you, actually. After we posted your talk, we had 400 people join the meetup group. So
wow,
you're definitely a very attractive speaker, I have to say. Well, thank you very much. And I'll see you guys soon.
Thanks a lot.
Thanks, guys. Bye, everyone.
Bye-bye.